of EMF sources, electromotive force, and which is basically battery is a classic example of an electromotive force, and internal resistance of battery and terminal voltage. These three concepts. EMF, internal resistance, and terminal voltage. So this section kind of goes kind of quick. We can use that simulation from yesterday. There was the so when we have the power supply, actually let's use a battery. So over here, we could get to choose the internal resistance of the battery. So if the battery is brand new, it's going to have an internal resistance of 0. So then when you connect it, so when you go to the voltmeter, you connect the battery. Well, it's a 9-volt battery, you see. Now, if I give it internal resistance, notice the battery is always going to show 9 volts, no matter what the internal resistance. So even if it's a very old battery, the internal resistance of the battery is like 10 ohms. When I hook up a voltmeter, it still shows 9 volts. This 9 volts is the EMF of the battery. It never changes. But the terminal voltage depends on what the circuit that I have it hooked up to. So if I connect it to a wire, and then let's say I've got a resistor, let's connect an ammeter. Okay, so imagine you've got the battery connected to 10. The battery has internal resistance of 10 ohms. Let's reduce the internal resistance. So let's say the internal resistance is 5 ohms. Now, if I connect the voltmeter across the battery, what is it going to show? Ah, I see, 6 volts. So the only way you know if your battery is bad, if it's used a bit, is to actually connect it to a circuit, you see. Oh, there's a voltage drop across the battery when I connect it. It's only 6 volts. This is called terminal voltage, you see. So now if the battery was brand new, what would happen? You see, the terminal voltage would equal to the EMF voltage if the battery was brand new. You see, so how does the equations of this work out? So when we can kind of write it like this. Imagine what we can write the battery like this: internal resistance, and then this is an external resistor. Okay, so then when you go across, this is the EMF. The EMF is what the battery is intended to give you. the electromotive force that the battery is intended to give you. And the electromotive force is measured in volts, so that you gain a certain voltage when you go from the negative to the positive. So let's say the current in the system is I, right? So then you have an internal resistance here. So you lose a little bit of voltage, IR internal, through the internal resistance of the battery. Then you lose a lot more voltage through the external resistor, minus IR, right? So I'm kind of applying the Kirchhoff's loop. So you just say you gain voltage minus IR int, right? This is the internal resistance, minus IR int, minus IR, and that's equal to 0. So to calculate the current in the circuit, you do what? You say EMF over the internal resistance plus the external resistance. EMF over the internal resistance over the external resistance. Okay, so now the terminal voltage across the battery is this part of it. So that means if I put a voltmeter across like this, and I test what the battery is actually giving you in that circuit, that's called the terminal voltage. So it's this part, EMF minus IR int. All right, so then when the internal resistance is 0, what happens? That means the battery is new. Internal resistance is 0. What's going to happen to the current? The current is always going to be just whatever the EMF of the battery is divided by the big R. Divided by the resistance that you have in the circuit. And the terminal voltage is always going to be what? EMF minus, if the internal resistance is 0, this part disappears, right? And then the terminal voltage is just the EMF. So essentially that's what that's saying is that if the internal resistance is 0, the current in the circuit, you see, is whatever the EMF is, 9 divided by 10. So 0.9, you see, 0.9 amps. And then the terminal voltage here is going to be always whatever the battery says it is, 9 volts. So even if I make this voltage some crazy number, let's see, how big can I make this? 120. See, the current came down, you see, got less, but the terminal voltage didn't change. Okay, but now what if I give this a slight resistance? Now let's say you've used the battery for 2 months. So 1 ohm resistance. Okay, now what happens to the terminal voltage? 8.93. Should we do the numbers of this? So you've got an internal resistance of 1 ohm on a 9-volt battery, and you've connected it to 120. So let's do that as an example.
Professor, quick question.
Yeah.
So you're saying that the resistance of a battery increases as it gets used, right?
Yes. Rust builds up or whatever, you know.
Oh yeah, because I was going to ask, like, what causes that specifically?
You know, it goes into the electrochemistry of how the battery is made, but the battery is forcing one of the plates to be cathode, one of them to be anode. And I believe there's, after a while, you get a mixture. So it's hard to maintain that pure cathodeness and pure anodeness. You get built up of negative charges on the cathode side and positive on the, which one's supposed to be the positive? Cathode? Right?
I think so.
Yeah, so whatever it's supposed to be, in other words, some charges leak to the other side. Plus, you get rust building up, depending on how the battery is made. So in essence, it loses the ability after a while to completely keep the two sides separate. A rechargeable battery is such that you can put it into the AC outlet, and the AC outlet runs the circuit backwards inside of the battery. In other words, it says, okay, all you negatives that have built up on the positive, get over to the negative, you know? So that's kind of what the rechargeable battery is able to do. You're sending all those stray negatives, go back to where you're supposed to be, kind of. You know?
Okay.
Yeah, you get that?
Yeah,
Okay.
that makes. Yeah.
Huh?
Yeah, I don't know. My connection was getting kind of weird. But yeah, that makes sense.
Yeah?
Yep.